Welcome back to Mechanical Engineering Made Simple. Today we're going to talk about something primal, fire. But more than that, we're talking about how we've managed to tame it, to capture its awesome power. We're going to dig into the basic rules that control everything from a tiny flame to a massive rocket engine, and we'll uncover the really surprising reason why we can never ever use all of its energy. So, where did this all start? Well, it really kicked off with this one simple but incredibly powerful idea. A French engineer, Sadi Carnot, put it perfectly. He wanted to capture the motive power of fire. I mean, think about that. For centuries, that's been the ultimate quest, right? To see the raw energy in a flame and figure out, how do I turn that into motion, into electricity, into, everything that makes our world run? But, and this is a big but, there's a catch. We've gotten really, really good at harnessing that power, but we've never, ever done it perfectly. Not once. Every single engine out there, I don't care if it's in your lawnmower or a jumbo jet, wastes a ton of energy. So why? What's going on? Why can't we just get out all the energy we put in? The answer, it turns out, lies in a couple of unbreakable laws of the universe. All right, so to really get a handle on this challenge, you gotta know the rules of the game. And when it comes to thermodynamics, there are two fundamental, absolutely unbreakable laws that run the whole show. Okay, I want you to think of it like this. You're in a cosmic casino. The first law, that's the main house rule. It says energy can't be created or destroyed. Basically, you can't just magic up more chips. So you can't get more than you start with. Simple enough. But then there's the second law. And this is where it gets really interesting. The second law says that every single time you make a bet, every time you convert energy, the house takes a little cut. A little bit of your energy just becomes, useless. So get this, not only can you not win, you can't even break even. And that right there is the fundamental reason why nothing, and I mean nothing, is ever 100% efficient. So this unavoidable loss, this cosmic tax we have to pay, it has a name. And honestly, it's kind of the main villain in our story. We call it entropy. Now, you've probably heard entropy described as just disorder or randomness. And yeah, that's part of the picture. But for us as engineers, there's a much more useful way to think about it. For us, entropy is a measure of energy that's no longer available to do useful work. Think about it like this. Imagine you have a nice, neat pile of sand. You can easily build a sandcastle, right? That's a low entropy state. Now, imagine that same amount of sand is scattered all over the beach. The sand is still there, the energy is still there, but it's so disorganized you can't do anything useful with it. That's a high entropy state. And look, this isn't just a nice story about sandcastles. This is hard physics, backed up by math. Just look at this equation. Now, don't get bogged down in the symbols, but I want you to focus on one part, that S-gen term. That stands for entropy generation. And what this equation proves is that for any real thing that happens, anything at all, that S-gen term is always positive. It's never zero, it's never negative, it's always going up. This is the cold, hard proof that every single process in the universe, from a star exploding to you just breathing, generates a little bit more of this useless energy. So, okay, what's the takeaway here? Just think of entropy generation as an unavoidable energy tax. It's a tax on every single energy transaction in the universe. When you burn gasoline in your car, you're converting chemical energy into motion, tax. When a power plant burns coal to make electricity, tax. You can't argue with it, you can't find a loophole, you just have to pay it. And really, you could say that the entire field of engineering is just one massive creative effort to minimize that tax bill. So if we're stuck with these laws, if we can't beat them, how do we design with them? How do engineers build these incredible machines, like a gas turbine in a jet, and still manage to harness all that heat so effectively? All right, let's peek inside a jet engine to see how it works. On the left, you have the compressor. Just picture a series of massive, powerful fans that grab air and just squeeze it hard. We're talking incredibly high pressure. It's like coiling a spring, just loading that air up with energy. Then, of course, we add fuel and light it up. That super hot, high-pressure gas has to go somewhere, so it blasts through the turbine on the right, spinning it like crazy and generating all that thrust. And this diagram is where it all comes together. It's called a temperature entropy diagram, or a TS diagram, and it's basically a treasure map for an engineer. It tracks the state of the air as it goes through the whole cycle. You can literally see the temperature and the entropy go up and down through compression, combustion, and expansion. And that big closed-off area in the middle, that's the money shot. That area represents the actual useful work we get out of the engine. So the entire job of a turbine designer, make that loop as big and fat as you possibly can. Okay, but it's not just about giant engines, right? These laws, this whole energy game, it reaches into everything. We're talking about the universal reach of thermodynamics. I mean, take the computer or phone you're watching this on. That little microchip inside, every single calculation it makes generates a little puff of waste heat. That's the entropy tax, right there. Now, multiply that by billions of calculations every second, and suddenly you have a serious heat problem. That's why we have heat sinks and fans. It's all just applied thermodynamics, a battle to get that waste heat away from the chip before it cooks itself. And then you can go to the complete other extreme, cryogenics. You know, the science of getting things unbelievably cold? It's literally the same principles, just running in reverse. Instead of using heat to create work, we're using work to pump heat out of a system. Your refrigerator does this, but cryogenics is like a refrigerator on steroids. We are actively fighting that natural flow of energy, yanking heat out of one place and dumping it somewhere else, all while that darn entropy is trying to leak back in. So after all this, what's the big takeaway? It's that the goal of engineering isn't to beat the laws of thermodynamics. We can't. There will never be a 100% efficient engine. A perpetual motion machine? Forget about it. The real point, the real art and challenge of engineering is to design the most efficient systems possible within those laws. It's about being clever, being creative, and figuring out how to squeeze every last bit of useful work out of the energy we've got. So the laws are fixed. The real engineering challenge is just how creative we can be inside those limits. It makes you wonder, right? Where else in our lives can we try to reduce that energy tax? And that's a challenge we all face every day. And hey, if you want to explore more challenges like this, if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.